Alright, so yesterday hopefully you watched a quick little introduction to Hess's law. So Hess's law is really just a way that allows us to calculate the enthalpy change or the energy change for a particular chemical reaction. So just in a real generic way, if we write A goes to B, whatever reaction that might be, if I tell you the delta H, and you'll see it written delta H Rx or delta H Rxn, whatever the enthalpy change for that reaction is, we should make up a number. We'll just say it's negative 20 kilojoules per mole. Just knowing that the delta H is negative 20 kilojoules per mole, what could you tell me about that reaction? So first, let's say it's exothermic. Then you could say, who was saying that? Yeah, lost energy. Okay, so energy is released. We know those two things already. So, for whatever reason though, transforming chemical A into chemical B might be complicated, or it could be a dangerous reaction for whatever reason. So if we could turn chemical A into some other chemical, do some other reaction, and then ultimately turn that into B. Instead of doing A to B, we go A to C, C to D, then D to B. What would the delta H for A to C, C to D, and D to B then become?
I don't know.
It's still just negative 20, because we still have the same reactant and the same product. Okay, so it doesn't really matter where we go in the middle of the reaction, but all that matters is the reactant and the product that we have. Okay, so we know this is an exothermic reaction. We know that energy is released into the surroundings. But then if I wrote this, if I wrote the reaction B goes to A, just based on the information you've already been given, could you tell me the delta H of the reaction, B turning into A? Yeah, it's positive 20, okay? And you don't have to write the plus sign, but it's pretty common to see these written as plus 20 kilojoules per mole. And obviously plus 20 and 20 are the same thing. It's pretty common to see the plus sign written in so you don't forget the sign. Okay? So if you flip a reaction, you just change the sign of delta H. Okay? So if A going to B releases 20 kilojoules of energy per mole, in order to turn B back into A, you have to then absorb 20 kilojoules per mole. Does that make sense? Mm-hmm. And so anytime we need to flip a reaction, we just change the sign, so we don't worry about any kind of multiplication or division or anything. So that is kind of Hess's law in a nutshell, the simplest part of it. So this ultimately will be one of the major goals of this chapter, is to calculate the enthalpy change for different reactions. Okay. In the notes it's typed delta HRX. I tend to write delta HRXN. Whatever you want to write there is fine. So we want to know, as we do a chemical transformation, do I absorb energy or do I release energy? And then, how much energy do I either absorb or release? Okay. So we have the formula from before on the first day. Delta H Rx, or delta H of a reaction, is just equal to the delta H of the products minus delta H of the reactants. Okay, we've already done that, or talked about it. A couple of new symbols we have in this. So the little degree symbol, it's not really a degree symbol, but we'll call it that for now, just tells us, among other things, primarily, that we're at 25 degrees Celsius. Okay? So don't get this mixed up with STP. STP is what temperature?
0 degrees Celsius.
So 0 degrees Celsius. So when you have the degree symbol, it's called a Plimsoll symbol. When you have the little degree symbol, we're in standard state, so 25 degrees Celsius. So why do we use the number 25 degrees Celsius? Yeah, it's about room temperature. Okay, so most chemistry that we do in the open room temperature. Okay, so we use that because it's pretty close to what we do most of the time. So that little degree sign doesn't mean a whole lot. It just tells you that we're doing this 25 degrees Celsius. So then, the sum of the products. So before we just said products minus reactants. The sum of the products, you have multiple products, just add them together. But then you have the little degree sign again, the 25 degrees Celsius. Then you have the subscript F. So the subscript F stands for formation. So we'll discuss that in just a minute. So now we have the delta H reaction equals the sum of the products, enthalpy of formation, minus the sum of the reactants enthalpy of formation. Okay? So the definition, or the enthalpy of formation, is typed out for you. So enthalpy of formation, or molar enthalpy of formation, is the enthalpy change, energy change, when 1 mole of a compound is formed from its constituent elements in their standard states at 25 degrees Celsius. Okay? So it's just how we make a molecule from its simplest parts. Okay? So if we think about just a random molecule, CH4. Okay? So let's try right here. What 2 atoms make up CH4, methane? Carbon and hydrogen. Okay? So carbon is what state of matter at 25 degrees Celsius? Now think about your pencil lead. Okay? It's a solid. So your pencil's just carbon, it's just graphite. It's not really lead. Yeah. So plus hydrogen, but hydrogen is not just H. How do I write hydrogen? H2. And at 25 degrees Celsius, H2 is a gas. Then I don't have room for an arrow. And then CH4 is a gas. So that is just the reaction for the enthalpy of formation for methane. But what I care about is the number. So if you go to the very last page of your notes, there is a nice table that gives us lots and lots of numbers. So these are all just delta HF values for a bunch of different compounds. Is CH4 even on here?
Yeah.
Yeah. So what is the value for the delta HF of CH4? Negative 74.9. So I can say delta H plus negative 74.9. Notice in the column headings, what are the units for all these numbers? Kilojoules per mole. Okay. So we balance this reaction. Put a 2 there. So what this is saying is that to produce 1 molecule of CH4 from its atoms at their standard state 25 degrees Celsius, we're going to absorb or release 74.9 kilojoules. We're going to release, and we have a negative delta H there. So we release that much energy. So you notice there's a bunch of compounds on here, but is this an exhaustive list of all the ones that exist?
No.
Obviously not, okay? But they all have a value associated with them. We just gave you some to look at. So for all these that we look at on here, they can all be produced just from simple atoms. We add them together. But if you look at some of them, we see some zeros on there. Tell me about the zeros. What are all the zeros on here?
BR2.
What do they have in common? They're just a single atom, okay? Unless they are what? Diatomic, okay? So all the ones that are zero are just single atoms if they're diatomic. But notice some of them have a zero option and a different option, okay? That depends on what? For bromine, what determines its value? Yeah, its state, okay? So it's matter phase. So notice all these are dependent on the state of matter, okay? So if you think about why these numbers are zero, so the delta HF just tells me the energy change when we form these. So aluminum solid, it's just aluminum solid, right? There's no way to form that from anything simpler, okay? Bromine liquid, there's no way to really form that from anything more simple. We have diatomic bromine. But bromine gas has a value because bromine is a liquid at 25 degrees Celsius. So at 25, or to go from bromine liquid to bromine gas, do I have an energy change associated with that? Yes. Okay. So all the ones that aren't zero have some energy change associated with them. So some are zero, some are positive, and some are negative. So typed out there, there's a few comments on what the signs mean. So it says, the more negative value, the more stable the material that is formed. The more positive the value, the more unstable. So let's think about why that might be really quickly. So let's just look at just real generically, A plus B yields AB. If I have a plus 275 kilojoules per mole. If I wrote it backwards, and I have AB yields A plus B, and this is delta H. Do I automatically know the delta H for this reaction?
Yes.
Yeah, what is it? Negative 275 kilojoules per mole. So in order to make AB, am I absorbing or releasing a lot of energy? I'm absorbing a lot of energy, right? So there is a lot of energy put into that molecule. So a lot of energy is associated with being unstable. And when it breaks down, is it going to release or absorb energy? It's going to release a lot of energy, okay? So the more energy that it takes to make a molecule, the more energy it's going to release when it breaks down, okay? So that's why we say the more positive the number for delta HF, the less stable it is. The more energy it's going to release when it breaks down. So there are a couple of examples typed out down here. For HI, gas, the delta HF is plus 65.4 kilojoules per mole. So it's a positive number. So when it breaks down, according to this reaction, we get hydrogen iodine solid. That's a very common decomposition there. So then the next one, C2H2. Is the delta HF there positive or negative? Positive. It's a pretty large positive number too, right? So when that breaks down, is it going to release a lot of energy? Yes. Okay. So that is a compound commonly used in welding. Okay? So it's a very high energy compound. Then the last one, HgC2N2O2. That's a polyatomic ion. Y'all didn't learn. The delta HF is plus 270 kilojoules per mole. So when we decompose or break down that molecule, are we going to release a bunch of energy? Yeah. If you ever watch Breaking Bad, there's a scene where they have a large explosion because of that. It's called mercury fulminate. So this is where, or using these reactions, are where all these delta HF values come from. Okay. If we could make water from its, where's water? From H2 and O2 and record the energy change, we would see this value right here, okay? And another thing to note is, this is not an exhaustive list, and you'll have the ones you need typically. But when we solve problems later, and we start using these values, if there's a number that you think you need, and it's not on this chart, don't assume that it's zero, but think, is the value zero? Okay? Think, is this a single atom, or is this a diatomic molecule at room temperature in the correct state of matter, okay? A lot of times it'll end up being zero, because there's no point in us typing like all the solid metals out and putting zero. We just put one or two to show you, but if I give you iron or copper or cobalt or magnesium solid, what is the delta HF value for that going to be? It's going to be zero, okay? So watch out for that, but don't just assume it's going to be. And there are some exceptions to that we'll talk about later if we have time. So now there's two different types of enthalpy change that we have. We have the enthalpy change for a reaction, and then we have the enthalpy change of formation, which is really just the energy change for a reaction when we form an element. So the same basic thing, just different names. So now, one more type of enthalpy change we'll look at is the enthalpy of combustion. So combustion is just a type of reaction, correct? So this is just a subset of enthalpy of reaction, okay? And while we classify it separately, a couple of reasons. First of all, anytime you combust something or burn something, are you absorbing or releasing energy? You're always releasing it, right? So the sign for delta H is always going to be what? It's always going to be negative, because they're always going to be exothermic. Okay, so we can say that this category of reaction will always have a negative delta H, because we're always going to release energy. So it's always going to be exothermic. And another reason is, I don't have to give you the entire reaction for a combustion reaction. I can just say the complete combustion of C6H6. Then can you supply the other reactant and the two products on your own? Yeah. So we just need one molecule to write a combustion reaction, okay? So because they're a little bit different, we have this new symbol. It's just delta H subscript C. Okay, so if you see that, Just know that is the enthalpy change for a combustion reaction. Nothing different. If you want to copy that down. Sometimes it's called the molar enthalpy of combustion because it's for the combustion of 1 mole. So if you go back in the notes, the next to the last page, there is a table for this. So, there. So heat of combustion, enthalpy of combustion, and the same thing here. So if I think to this chart, the delta HF chart, for this number, negative 127, this is the energy change when I form AgCl from silver solid and chlorine gas. Right? It's just making it from its individual pieces. These values are not the energy change when you make it from individual pieces. These values are the energy change when you do what? Yeah, when you combust it. Okay? When you react it with oxygen and produce CO2 plus H2O. Okay? So make sure you know the difference in these two tables. They're still delta H's. They have the same units, kilojoules per mole, but they refer to different situations. The formation table refers to the energy change when you make it from its simplest elements. This table refers to the energy change when you combust it. Okay? Again, this is not an exhaustive list, but it's some of them. Okay? If you look at all these numbers, they all have what sign? Negative. So all combustion reactions are endo or exo. Exo, they're all releasing heat. Okay? So just using this table alone, could you tell me how much energy is released when 1 mole of hydrogen gas is combusted? Yeah, what's the answer? So we don't release negative 285, we release 285.8 kilojoules. Okay? If you say you release negative, it kind of implies you absorb. Okay? So the negative tells me I release, the number tells me how much I've released. Okay? So 1 mole of CO, when it burns, it releases 283 kilojoules. Okay? Could you also figure out how much energy is released when half a mole burns? Yeah. Could you figure out the energy released when 25 grams burns? Yeah, you can convert from grams to moles, and then from moles to kilojoules here. Okay? Also notice here, though, all these have state symbols as well. So there might be a different value for carbon monoxide solid or something. Okay? So some of these, are any of these repeated? Maybe not in this chart. But in other charts you'll see you might have a liquid and a gas option per molecule. So it's very easy to get messed up by just looking for CH4 and grabbing the first one without checking the state of matter. Okay? A lot of times you get it right, but sometimes there are two. Okay? Especially in the formation enthalpy chart. Water is the common one that's messed up. Most of the time we deal with water in what state of matter? Liquid. And I think in this chart, if we turn to the back, we probably have 2 or 3 values. So we have 2. Notice which one is listed first, liquid or gas? Gas. So if you're just scanning, see water, grab that number, are you going to get it correct? No. Also, what's right above H2O gas? H2O2 liquid. Okay? So it's kind of sad if you mess up on the test pretty badly because you know what you're doing is to pick the wrong numbers out. Okay? So be sure you pay attention when you're using these numbers in a minute to grab them. Okay? So now we have 3 different enthalpy change types. Enthalpy change of reaction or enthalpy of reaction. Then combustion enthalpy or enthalpy change during combustion. Those two are really just the same thing. We just classify combustion separately. Then we have the formation enthalpies, which we use with this formula to calculate the delta H of the reaction. Okay? Any questions so far? So let's look at why I need this now, why this is useful. We'll turn over to the back. So let's read the question. Calculate the standard delta H Rx for the following reaction. 1 mole of calcium carbonate decomposes into solid calcium oxide and carbon dioxide. So this probably should seem like a pretty logical question to ask. When calcium carbonate decomposes, how much energy is either absorbed or released? That's something useful to know. So we don't have a special table for decomposition enthalpies. Okay? So we got to use the formula. So to calculate the reaction enthalpy I need what values for the products and reactants? Yeah, the formation enthalpies. Where do I find those? The back. So go ahead and find those and copy those onto these 3 lines. And obviously on the test you'll have these. Make sure you grab the correct sign too. For some reason that's always the hardest step for people. Getting the correct number out of the chart and writing it down. Isn't that right, kind of big? All these numbers have what units? Kilojoules per mole. I'll just put it at the end. I ran out of room. So my formula for delta H reaction equals sum of product delta HF minus sum of reactant delta HF. So I can just say delta H reaction is the sum of the products. So what are my 2 products? Right here. So I add those 2 together. Negative 634.9 plus negative 393.5 minus negative 1207.6. And this is very, very easy because you're just adding and subtracting, but it's really easy to mess the signs up. So be sure you pay attention to your signs here. So go ahead and type in the calculator to make sure you can get that. It's very easy to screw these signs up when you're doing this. You should get the answer at the top, hopefully. Anybody get it?
I did.
So the units, I should have written them in the whole way, but I didn't, are kilojoules per mole. When you add and subtract the same unit, do they cancel? Now 5 grams minus 3 grams is 2 grams. They don't cancel when you add or subtract. So that is the delta H standard value. Could I then ask you the delta H for 1 mole? Would that be the same number? Yeah. If it's that many per mole for 1 mole, it's the same number. If I ask you for half a mole, you get multiplied by 0.5. Okay. So one little shortcut you can take, if you're always doing products minus reactants, could you always just change the sign of the reactants and add across? Yeah. So really here, all this subtraction does is change the sign of the reactants. Okay. So if you want to just shortcut that, you can. If that doesn't make sense, don't worry about it. And this reaction is simple because it's already balanced, right? So I have a 1 there, a 1 there, and a 1 there.
And if it's not balanced, then you have to multiply.
Yeah. So if it weren't balanced, you have to multiply with the coefficients, just like always. It's easy, though, to forget to balance on these. Okay? So that's something very simple but very important. You cannot forget to balance your reactions. Okay? You don't want to go through the proof of why this works, or just trust me? Just trust me? Okay. That's fine. We'll do the proof for the next one. Any questions about that? Okay, pretty straightforward. Easy calculation. It's very easy to mess it up, though. A lot of signs, a lot of subtracting. People always get that wrong in the calculator. Okay? Then I could ask you in words, is this reaction endothermic or exothermic? Endothermic. And I could say if you have half a mole or 15 grams, how much energy is released? And I could say, is energy released or absorbed? So there'll be several follow-up questions to this. Okay? So, 2. Calculate the standard delta H Rx for the combustion reaction of 1 mole of methane gas. So, because it's combustion, could I just go to the enthalpy of combustion table and find the delta H for the combustion reaction? Yeah. But this, let's pretend we don't have that right now. This is showing you where it comes from, okay? So just be aware, if it's in the chart, which it is, you could just grab that number and be done. But for one that's not in the chart, we couldn't do that, okay? So let's go through if we don't have the chart. So the first step, as with all problems, have always been, is to write the reaction. Then do what to the reaction? Balance it. Here, state symbols start to matter though. Okay, so it tells you CH4 is a gas. What do I add?
O2.
O2, what state of matter?
Gas.
Gas. What do I produce?
CO2.
CO2 gas and H2O liquid. Then the easiest thing to mess up is to not do what now? Balance it. Okay, so 2 there, 2 there. Then what's my next step going to be? You go to the back and find the, what are the thingies called?
The chart thing.
What are they called? What are they?
The enthalpy.
Enthalpy of formation. So go find your enthalpies of formation. I'll put blanks for you. Which one can you not worry about or just skip? Oxygen. I think it's in our chart, but if it weren't, you could skip it because it's 0. Because oxygen is diatomic.
Wait, so if it's just one atom and it's not connected to another one,
If it's in the correct state of matter, yes.
okay.
For H2O, do you have the challenge
Yes, sir.
for H2O, do you have the
Just write the number in from the chart for right now. So just copy the number straight in. What's the value for CH4? Forgot to write it down. I heard like 3 different numbers.
That's the S.
74.9. So if you found negative 890.2, you looked in what chart instead? The combustion chart. We need the formation enthalpies. Okay. The negative 890.2 tells me the enthalpy change for this whole reaction. Okay. But we're assuming or pretending we don't have that value available to us. And I didn't write it in, but all these have what units? Kilojoules per mole. So now can I just plug in products minus reactants again? Yeah. But the one thing is, I've got to do what to negative 285.8? Multiply by 2. Do I care about this 2 right here? No, because it's 0. Okay. If you want to plug in 0, you can, but you're just adding zeros, so don't worry about it. Okay. So plug in products minus reactants and see what you get. Yeah.
When you multiply by 2, you keep the sign.
Yeah, so it's just 2 times negative 285.8. And you should get negative 890.2. And I didn't write the units in because there's not room for me to write. Make sure you have the correct units on your final answer too. So if you want to do the shortcut, just say positive 74.9 minus this number, parentheses times 2. If that doesn't make sense, just don't worry about it. Are we getting that number? If you didn't get it, type it in again.
Wait, I got negative 891.9.
You must have hit a wrong key somewhere along the way.
I did 74.5 for negative 74.9.
No, I did it right.
I got 253.
Keep typing it in.
It's when you multiply the negative 285 times 2, it makes it positive, so yeah.
Isn't it just 570?
So if you're messing up, get your neighbor to show you how to use the calculator.
No, you don't
Isn't it negative 571.6?
No,
Yeah.
it is a negative.
Then why did I get negative, why did I get, what? I'm thinking, 285. Mr. Franklin.
Yeah.
I'm doing that.
All right, guys, let's have calculator time. So, guys, hush. So look at me. So I'm going to do products minus reactants. So I'm going to go ahead and do 2, can y'all see this calculator? 2 times negative 285.8. Okay. Is there any need to write that number down? Probably not. Okay. I'm going to add this number. So plus negative 393.5. So I get that. Then minus this number. So when you subtract the negative, what are you going to do to it? So I can type in minus negative, or I can just type in plus. Plus 74.9. Okay. If you want to type in minus and negative, your calculator can do that, but it's easier to mess up hitting a key. I don't like doing minus negative, just do plus. Yeah.
So why is it minus plus negative 290? How is minus negative?
No, because it's the sum of the products and sum of reactants. So sum means that, just add them together.
Alright.
Yeah, I got the answer I thought it, so I don't know what happened.
Yeah. We'll try, make sure you can type it in and get it right. Okay. So that is always complicated for people, is make sure you can use the calculator properly. Okay. Other than calculator issues that you can resolve later, any question about it, set that up. That's what we're more concerned about. So let's look at kind of how this works or why this works for a second. So we're trying to figure out the enthalpy change for this reaction. So if you look it up in the table, it matches our answer for the combustion. But we're using the formation enthalpies. Okay? So let's look at this number right here to start off with. This number is the enthalpy change for the formation of CO2. Right? So what does the formation of CO2 look like? How do I form CO2? Carbon plus O2 yields CO2. This number is for the formation of water. How do I form water? H2 plus O2 yields H2O. Is that balanced though? No, so I put a 2 there. I put a 2 there. So I can write these numbers in. This number was negative 393.5 kilojoules per mole. This number was 2 times negative 285.8 kilojoules per mole. Do I worry about the formation of oxygen? 0. So then I have the formation of CH4. That looks like C plus H2 yields CH4. And I balance it. I put a 2 there. But here, let me write the number in. It's negative 74.9 kilojoules per mole. Here I'm producing CH4. Up here, is CH4 a product or a reactant? Reactant. So can I flip this equation if I change the sign? Yeah. So I can write CH4 yields C plus 2H2. And what is the value for this delta H? Yeah, plus 74.9. I'm going to cross this one out because I'm done with it. I flipped it. So now let's look at what cancels out. So if something's in the product and reactant side, it cancels. So I have carbon is a reactant and carbon is a product. Do those cancel? Yeah. Cancel that. I have two H2s. Two H2s. Do those cancel? Yeah. Does anything else cancel? No. So if I added these reactions together, I get CH4 plus 2O2 yields CO2 plus 2H2O, which is the reaction I was talking about. Okay. So using the enthalpies of formation, it just gives us a way to basically recreate the reaction by using these numbers. So now, if I took the sum of all these numbers, what am I going to get? Negative 890.2. That's essentially what we did. okay? This what I just did was kind of the long around the multi-step way of doing the simple calculation, okay? So that's why using these delta HF, enthalpy of formation values, work when we're trying to find the overall enthalpy of reaction, okay? It just gives us a multi-step way to accomplish this reaction, okay? Any questions about that? Okay, good. Now let's look at example 3. Calculate the standard enthalpy of formation for 1 mole of pentane. So, for the enthalpy of formation, I can go to the delta HF table and find it. But pentane is not in that table. Our table is not an exhaustive list, so we don't have a way to find it. So, first let's write what I'm looking for. I'm looking for the delta HF for pentane, C5H12. What does that reaction for the formation of pentane look like? Bless you. What does the formation of pentane look like in reaction form? Yeah, just C plus, not just plus H, plus H2 yields C5H12. So I just balance it, 5 and 6. So when I ask you for the enthalpy of formation for pentane, I'm just asking you what is the energy change when this reaction happens. Okay? Normally that comes from the chart, but we don't have it in the chart. We've got to find a different way to solve it. So we don't have the formation enthalpy for pentane, but we do have a different enthalpy change for pentane. Okay? What is that value? What is that called? The combustion enthalpy, yeah. So is there a combustion enthalpy for pentane? Yeah. So let's write the combustion reaction. What is the combustion reaction for pentane? C5H12 plus O2, what state of matter? Gas plus CO2, gas plus H2O, liquid. Does the order matter? No, it really doesn't matter.
Wait, what's the state of matter of C5H12?
What does it say in the table? It's probably a liquid. It should say in the delta HC table. It's a liquid though. Okay. So, do I know the delta HF for pentane? Is it listed as a gas? Okay. So whatever it is, no, it doesn't matter because we aren't finding the delta HF for that, or we are finding it. We're not given that. Do I know this value? No. If I knew the value, would I be doing this? No, I'm trying to find that. Do I know the value for O2? But do I care about the value for O2? No, just 0. Then either from the delta HF table or the previous problem, copy these numbers down. CO2 is negative 393.5 kilojoules per mole. Then H2O is negative 285.8 kilojoules per mole. What is the enthalpy change for this reaction? Yeah, but what is the value from the table though before we do? Negative 35.6 kilojoules per mole. So that is the enthalpy change for this combustion reaction. And what have I got to do before I get too carried away and forget to do it? Balance it. Okay. So balance that real quick. We're kind of low on time, so I'll just tell you. It's 1, 8, 5, 6. That's how you balance that. Okay. So there's two ways to solve this. The first way, if I know the delta H of the reaction, I know the delta H for the products, can I then solve for the delta H of the reactant? Yeah, I can just plug in. Okay, so we can do that. Let's look at the longer way to see how that works though. So ultimately what I have to do is I have to recreate this reaction by using this reaction. Okay? So the first issue with turning this into this is where pentane is, right? Here pentane is a reactant. I want it to be a product. So how can I, or can I flip a reaction? Is that legal? Yeah, just do what to the delta H? Change the sign. let's rewrite it. Let's say 5 CO2 plus 6 H2O yields C5 H12 plus 8 O2. Then what is the value of the delta H for this reaction? Positive 35.6 kilojoules per mole. Okay. So if I'm ultimately trying to turn this into that, does the formation reaction have CO2 in it? Does this reaction have CO2? No, so I got to cancel out CO2. How many CO2s do I have to cancel? 5. So let's just put 5 CO2s over here. How do I make those 5 CO2s? What is the formation reaction? Yeah. C plus O2, and I balance it, 5 of these, 5 of these. Do I have a delta H value for carbon plus oxygen yield CO2? Yeah. But what have I got to do to that value now, though? Multiply by 5. So now, let's address water. Is there a water in this formation reaction I'm trying to make? No, so I've got to cancel it. So I have 6 waters. So let's get rid of 6 waters. So I write the formation of these waters. So I have 6 H2 plus 3 O2. Do I have a value of the energy change when I have H2 plus O2 yields H2O? Yeah. What do I have to do to that number, though? Multiply by 6. So I have 6 times negative 285.8 kilojoules per mole. So now let's check our progress. So I have 5 carbons over here. Doesn't cancel anything, so I can't do anything with that. I have 5 CO2s here, and I have 5 CO2s there. Do they cancel? Yeah, one product, one reactant. Now I have 6 waters in the product, 6 waters in the reactant. Do they cancel? Yes. I have 8 O2s in the product side. How many on the reactant side?
No, you have 8.
I have 8. That cancels. So now, if I add up everything that did not cancel, I have 5 carbons plus 6 H2s yield C5 H12. Is that what I'm trying to produce? Yes. So if all these reactions add up to this reaction, are all these enthalpies going to add up to be the enthalpy change for this reaction? Yes. Do I have to do any negative positive switching or anything? I already did that when I flipped the reaction, okay? So just add these. 35.6 plus negative that number plus negative that number. Don't forget to multiply by 5 and by 6. And your units are going to be what?
Kilojoules.
Kilojoules per mole. When you add and subtract, they don't cancel, okay? The enthalpy of combustion table.
Okay.
So this was the long way. The short way, you could just said negative 35.6 equals sum of products minus sum of reactants, which is really what I did by doing this. You flipped the sign of the reactants, added the products. Okay? So either way, you get the same answer there. So then you have, what'd somebody get? 46.7 kilojoules per mole. Okay. Questions about that?
How do you cancel it again? Can you, sorry, I was...
So 5 CO2s in the reactants, 5 CO2s in the products.
And it doesn't have to cancel throughout all 3?
No, just if it's always on the reactants and product side, it cancels.
Okay.
Yeah. Any other questions? That's enough chemistry for one day, then. We'll call it a day.